This is Climate Watch. I'm Zhao Ying. Welcome to the show. Do you start your day with a cup of coffee? Globally, we brew our way through more than 2 billion cups every single day. But have you ever wondered what happened to those grounds once your cup is empty? Every year, we generate 10 billion kilograms of spent coffee waste. Most of it ends up in landfills, where it rots and pumps greenhouse gases like methane and carbon dioxide into the atmosphere. We often say waste is just a resource in the wrong place, and now scientists have found a way to build a greener future. Researchers using coffee grounds can create a substance that can replace up to 15% of the sand in concrete. This doesn't just make the concrete 30% stronger, it also slashes its carbon footprint by up to 26%. Today, I'm joined by one of the scientists behind this breakthrough, Dr. Zhang Jingxuan from the School of Engineering at RMIT. She leads the life cycle assessment on how coffee waste helps make lower carbon concrete. Hi, Jingxuan. Thank you so much for joining us.
Thank you so much for having me.
Most people may have no idea just how big a climate villain concrete actually is. Can you help us understand why making concrete releases so much carbon dioxide in the first place?
To really understand concrete's carbon footprint, it is worth stepping back and looking at the big picture. Over billions of years, the Earth has naturally regulated carbon through geologic processes. Things like weathering, sedimentation, and the formation of limestone. Carbon has been slowly locked into rocks, oceans, and the Earth's crust over extremely long time scales. What humans have done in the last century is not just create a new carbon problem, but dramatically speed up natural processes. Concrete sits right at the center of that acceleration. It's everywhere. It's the second most used material on Earth after water. Because we rely on it so heavily, even small changes in how we make concrete can have very large climate impacts. Concrete itself is made from stones, sand, and cement. The stones and sand don't carry much carbon, but cement does. Making cement requires extremely high temperatures. When the limestone, which is the primary ingredient of cement, is heated in the kiln, CO2 is released as part of the chemical reaction, not just from fuel, but from material itself. Even after cement is produced, when it reacts with water during construction, additional emissions are associated with the process. That's why every kilogram of cement we produce, roughly 0.9 kilograms of CO2 is released. In other words, cement production brings geological carbon into the atmosphere on a human time scale. That's why concrete has a large carbon footprint. Not because it's unnecessary, in fact, it's essential, but because we use it on a huge scale and produce it very quickly. So the challenge we face is not to stop using concrete, but to understand how we can slow down and reduce the carbon impact of this process while still building the cities and infrastructure that society depends on. So concrete is absolutely essential for modern infrastructure, but it's also one of the biggest contributor to industrial carbon emissions.
Yeah, so it has such a huge carbon footprint, yet most people wouldn't look at a pile of wet coffee grounds and think construction material. So what first led your team to explore coffee waste as an ingredient for concrete?
Our team at RMIT, led by Professor Jie Li, works on making construction more sustainable. We focus on utilizing recycled materials and minimizing waste to produce greener concrete and roads. Over the years, we developed eco-friendly concrete using various waste materials and industry byproducts, such as old tire, old concrete, crushed glass, fly ash, and other organic waste. So you can see a big part of our research looks at circular economy, which simply means asking once something becomes waste, can it be reused in a better way instead of going to landfill? In my own work, I focus on understanding how different recycling pathways affect environmental outcomes. For example, how waste is collected, how it's produced, and where it finally ends up can make a big difference to its carbon footprint. The idea of coffee waste came up very naturally during a casual coffee break. Australia throws away around 75,000 tons of used coffee grounds every year, and most of it ends up in landfill. In a city like Melbourne, where coffee is part of daily life, we started asking a simple question. Once coffee grounds become waste, can they be redirected into construction instead of landfill? That question fits directly into our broader circular economy research, and that's how biochar coffee concrete idea begins.
Okay, that's really interesting. But for listeners who may not be familiar with biochar, can you explain how you turn coffee waste into this carbon-rich material?
We often joke in our group that making concrete is actually quite similar to cooking or baking. You are not just putting ingredients together. You need the right conditions, the right temperature, and the right balance to get a good performance. For this particular recipe, we start with using coffee ground, which would otherwise go to landfill. Instead of burning them, we heat them. A little bit like roasting, but in a low oxygen environment. At around 350 degrees Celsius, the coffee grounds are transformed into a stable, black, carbon-rich material. Because it comes from organic waste, we call it biochar. A simple way to think about biochar is like it's similar to charcoal people use for barbecues. The key difference between these processes and normal burning is oxygen. When you burn something in air, the carbon reacts with oxygen and escapes as CO2 into the atmosphere. In our process, because it's very little oxygen there, most of the carbon remains stored in the solid material rather than being released as emissions. From a climate perspective, that's important because we're retaining biogenic carbon in a stable construction material instead of allowing it to be released into the atmosphere through landfill or burning.
Okay, well, your earlier experiments showed that replacing just 15% of sand with coffee biochar increased concrete strength by nearly 30%. Well, that's really amazing. Why does biochar have this effect?
Making concrete sometimes feels a bit like baking. To get a good strength, you need just right amount of moisture. Too much water isn't ideal, but being too dry is even more limiting, because the cement simply can't fully react. Biochar helps address that problem. You can think of it as being similar to the activated charcoal people use in refrigerators or wardrobes for moisture or odor control. If you look at it under a microscope, you will see that it has a lot of tiny pores inside, which allows it to absorb water and store water. When biochar is mixed into concrete, it acts like a small internal water reservoir. As the concrete starts to dry from the inside, the biochar slowly releases the stored water. This process is known as internal curing, and it helps the cement hydrate more completely over time. In our study, we replaced the sand with biochar based on volume rather than weight, because biochar is much more lighter than sand. That way, we maintained a comparable mixed structure while still benefiting from the internal curing effect. At around 15% replacement, we found a sweet spot. Strong strength gains without compromising workability or stability.
Okay, and your new study adds something really important because you did a full life cycle assessment. Why is life cycle analysis such an important step, and what does it tell us that lab strength tests alone can't?
In the lab, we usually focus on how strong concrete is, things like compressive strength or durability. Those tests are essential because they tell us whether a material is safe and fit for use. But sustainability is a very different question. A material can be strong and still have a large environmental footprint. That's why we use a method called life cycle assessment, or LCA. LCA looks at the environmental impact of a material across its entire life, where the raw materials comes from, how they are processed, how far they are transported, and how they are used on site, and what happens at the end of their life. In other words, it helps us understand the whole system, not just what happens in the laboratory. This is particularly important for recycled or waste-based materials. Sometimes the material looks very green in the lab, but once you include energy use, transport distances, and processing steps, the environmental benefits can shrink or even disappear. A big part of my own research focuses on monitoring and comparing different circular economy pathways, essentially asking how different pathways of recycling or reuse waste affect real environmental outcomes. In this study, LCA allowed us to answer a very practical question. Compared with conventional concrete, does biochar concrete still reduce carbon emissions once we account for real-world facts like energy use, logistics, and end-of-life treatment? Without LCA, we could only be telling a part of the story. With it, we can assess whether a new material is not just strong and innovative, but generally lower carbon when scaled up for real construction.
Okay, but when you say life cycle, what exactly does that mean in this context? Like, does the cycle start from growing the coffee beans or when the used coffee grounds become waste?
When we talk about life cycle in life cycle assessment, what we really mean is the full sequence of environmental impacts associated with the product or material, from a very clearly defined starting point to a clearly defined endpoint. One of the most important and sometimes most misunderstood parts of LCA is deciding where the system boundary begins. In our study, the life cycle starts at the point where used coffee grounds become waste, not at coffee farming or roasting. The reason for that is very deliberate. Our research does not change how coffee is grown, processed, or consumed. People will continue to drink coffee. Cafe will continue to use coffee grounds, regardless of whether our technology exists or not. So instead of asking whether coffee itself is sustainable, we're asking a different and more practical question. Once coffee grounds become waste, what's the most environmental responsible ways to handle them? From that point onward, there are several possible pathways. One option is landfill, where organic waste like coffee grounds goes to landfill. It decomposes and may release methane, which is a very powerful greenhouse gas. Landfill also involves ongoing transport, handling, and disposal costs. Another option is energy recovery, where the waste is burned to generate electricity. While this can offset some fossil fuel use, the carbon stored in the waste is still released directly into the atmosphere as CO2. The third option, which we'll explore in our study, is circular use. We convert the waste into biochar and use it in concrete, where it replaces a part of sand and indirectly reduces the demand of cement. This pathway avoids landfill emissions and reduces the extraction of processing of virgin construction materials. By defining the system boundary at the waste stage, we can make a fair apple-to-apple comparison between these different end-of-life options. We're not comparing coffee versus no coffee, but comparing what happens after coffee has been already consumed. From a circular economy perspective, this is a very important distinction. It shifts the focus away from consumer behavior, which is often hard to change, and towards waste management and material reuse, where engineering and policy decisions can make a real difference. In that sense, the life cycle assessment helps us evaluate not just the material, but decision pathway, landfill, burning, or circular use, and identify which option leads to the lowest overall environmental impact.
So what were your main findings, and what surprised you the most when you saw the final numbers?
Our main finding was replacing sand with coffee biochar in concrete led to very consistent and meaningful environmental impacts. Specifically, we observed life cycle CO2 reductions of around 15%, 23%, and 26% when 5%, 10%, and 15% of sand was replaced with biochar. At the same time, fossil fuel use dropped by up to 31%, and we also saw improvements in impacts related to freshwater ecosystems. What really stood out to us was not just the size of the reductions, but how robust they were. In many studies, environmental impacts look promising at the lab scale. But once you include real-world factors, such as energy required for processing, transport distances, and what happens at the end of life of a material, those benefits often shrink or disappear. In our case, that didn't happen. Even after we accounted for energy used to produce biochar, the logistics involved in moving materials, and realistic end-of-life scenarios, the overall environmental gains remained strong. That was the most surprising and encouraging part of the study. It told us that this is not just a lab result or theoretic calculation. When we looked at the entire system, the materials still delivered meaningful carbon reductions. So the numbers confirm that this is not just an interesting idea on paper. When evaluated at the system level, it holds up as a credible circular economy solution for the construction sector.
Okay, so you achieved up to 26% life cycle CO2 reduction and 31% less fossil fuel use at only 15% sand replacement. Walk us through where the biggest emission savings come from.
The emission savings mainly come from two different but connected sources. The first one is performance-based. Because the biochar concrete is stronger, we don't need as much cement to achieve the same structural performance. In practice, that means we can reduce the overall volume of cement required. Cement has the highest carbon footprint in the concrete mix, so even at a modest reduction in cement demand, leads to a large reduction in emissions. The second source of savings is material-based. By replacing part of the sand with biochar, we reduce the need for sand extraction, processing, and transport. Although sand might seem like a low-impact material, extracting and moving large quantity of sand does carry significant environmental and energy costs. What's important here is that these two effects together. We're not just swapping one material for another. We are improving performance at the same time. That's why, even at a relatively low replacement level of 15%, we still see life cycle CO2 reductions of around 23%. In other words, the savings come from both using materials more efficiently and using lower impact materials, which is why the results remain meaningful when we look at the full life cycle.
So if we want to scale this up for real-world construction, do we actually have enough coffee waste to support large-scale production? And what challenges might we face, for example, in collecting and transporting all the waste?
That's a very common and very reasonable question, and it's usually the first thing people ask when they hear about waste-based materials. In terms of quantity, coffee waste itself is not a limiting factor. In Australia, we generate around 75 million kilograms of spent coffee grounds every year, and most of it currently ends up in landfill. Globally, the amount exceeds 10 billion kilograms annually, so from a purely material availability point of view, there is more than enough coffee waste to support large-scale applications. But coffee is really just the starting point. Our border research looks at how the same biochar approach can be applied to other organic waste streams, such as food waste, and agricultural residues. That means we are not relying on a single waste source. We are exploring a whole family of materials within a circular economy framework. In practice, the real challenge isn't whether we have enough waste. The challenge lies in collection, processing, and logistics. Coffee waste is generated in many small locations, cafes, restaurants, offices, so collecting it efficiently requires coordination, infrastructure, and sometimes changes to existing waste management systems. Transport distances, contamination, and consistency of supply all need to be carefully managed. These are not laboratory problems. They are system-level and supply chain challenges. That's why scaling up isn't just a technical issue. It's about collaboration between researchers, industry, waste managers, and local governments. At the moment, we are actively looking to work with industry and government partners on pilot projects, product development, and real-world trials to understand how these supply chains can be operated at scale. If we get that right, coffee waste and other organic waste streams could become a reliable input for low-carbon construction materials rather than something that simply goes to landfill. So in short, the feedstock is there. The next step is building the systems that allow us to use it efficiently and responsibly.
Are there construction companies or government showing interest in adopting this technology? Like, what kinds of conversation are you having with industry partners at this stage?
Yes, we're already seeing strong interest from both government and industry, and in fact, this technology has moved beyond laboratory and into real construction projects. In May 2024, RMIT partnered with the Macedon Ranges Shanghai Council to build the world's first footpath made with coffee biochar concrete in Victoria. That project was important because it showed local councils that this material could be used safely and practically in everyday infrastructure. Building on that success, in September 2024, Major Road Projects Victoria and Build Group adopted the same technology for the Pakenham Roads upgrade, a project valued at more than 400 million Australian dollars. That project used around 5 tons of spent coffee grounds, which is equivalent to roughly 140,000 cups of coffee. What's significant here is the progression. We moved from a smaller scale council project to a major state infrastructure project, which shows the growing confidence from industry and government. In our conversations with industry partners, the questions are no longer does this work? Instead, they are asking practical questions like how can this be supplied at scale? How do we ensure consistent quality? And how can these be integrated into existing construction standards and procurement processes? At RMIT, we are actively working with industry partners to address these questions and to explore pathways for commercialization and standardization. That includes understanding supply chains, performance requirements, and how this kind of technology can fit within existing regulations. So the interest is very real. The next phase is about turning these early projects into repeatable, reliable solution that industry and government can adopt more broadly.
So we know that concrete is responsible for about 8% of global CO2 emissions. But in your view, how big a deal could waste-based biochar replacements realistically be in cutting that number?
Concrete is responsible for roughly 8% of global CO2 emissions, so it's important to be realistic about what any single solution can achieve. Waste-based biochar is not a silver bullet that will eliminate all of those emissions, but it can play a meaningful role as part of a broader decarbonization strategy for the construction sector. From our preliminary studies, we see that Australia generates enough organic waste that, in principle, it could be repurposed into biochar for use in construction materials. The quantity is actually comparable in scale to current sand use in concrete production, which is significant from a material perspective. Australia produces around 10 million tons of cement every year. Cement is the most carbon-intensive component of concrete, so even partial reductions in cement demand, achieved through stronger or more efficient concrete mixes, can have a meaningful national impact. What's important is that this approach works on two levels at the same time. It helps reduce emissions from waste management by diverting organic waste away from landfill, and it reduces emissions from construction materials by lowering the demand of virgin resources and cement. In practice, that means the impact is cumulative rather than isolated. You're not just reducing emissions in one sector, you are actually linking waste management and construction into a more circular system. So while waste-based biochar won't single-handedly solve the 8% problem, it presents a practical, scalable tool that can contribute to real emissions reductions, especially when combined with other measures like low-carbon cement, better design, and more efficient use of materials. From an engineering perspective, that's often how progress happens, not through one dramatic solution, but through many smaller, credible changes that add up at scale.
Okay, and since biochar is gaining so much attention globally, do you see other types of organic waste becoming construction materials in the future?
Absolutely. What we're seeing globally is growing interest not just in biochar itself, but in how organic waste can be transformed into construction materials more broadly. Biochar is not a single product. It's a platform technology. It allows different types of organic waste to be converted into stable, carbon-rich materials that can potentially be used in construction. In our work, coffee waste is just one example. Just like what I mentioned, we are now applying similar technologies to other organic waste streams, such as food waste and agricultural residues. However, this is where life cycle assessment becomes critically important. Not every waste material will automatically lead to environmental benefits just because it's recycled. Different waste streams require different levels of processing, energy input, transport, and handling. Without LCA, there is a real risk of assuming something is sustainable simply because it comes from waste. Life cycle assessment allows us to compare different recycling pathways in a consistent way. From an engineering perspective, that's essential. Future construction materials are unlikely to rely on a single hero waste material. Instead, we expect a portfolio of waste-based materials, each suited for different performance and environmental goals. Life cycle assessment gives us a way to make those decisions properly. It helps make sure new materials don't just work in theory, but actually reduce carbon emissions when they are used in real world. So while coffee biochar is an important starting point, the bigger picture is about using tools like LCA to responsibly integrate a range of organic waste streams into construction in a way that truly supports a circular economy.
So if people listening wanted to help make projects like this happen, whether as cafe owners, engineers, or just coffee drinkers, what's the first thing they could do?
We're not trying to tell people how much coffee they should or shouldn't drink. That's really a question for nutritionists, not engineers. What we do hope for these is something much more simpler and much more practical. Whether you're a cafe owner, engineer, or just someone who enjoys a cup of coffee, keeping waste streams clean and properly separated makes a real difference. When organic waste like coffee grounds is kept separate from general waste, it becomes much easier to collect, process, and turn into useful materials like biochar. Better source separation improves efficiency, reduces contamination, and ultimately lowers the environmental footprint of recycling. These might seem like small actions at the individual level, but at system level, they have a big impact. They help close the loop between everyday behavior and what we can realistically achieve in construction and infrastructure. For those who work in industry, local government, or waste management, collaboration is especially important. Scaling up solutions like these depends on supply chains, logistics, and real-world trials, not just laboratory research. If anyone is interested in cooperating on supply chains, pilot projects, or field deployments, we'd be very happy to hear from you.
Dr. Zhang Jingxuan from the School of Engineering at RMIT, thank you again for joining us today.
Thank you again for having me.
And that wraps up this edition of Climate Watch. You can find more episodes on your favorite podcast platforms. Just search for Climate Watch and hit subscribe. Don't forget to leave us a quick review or share it with a friend. You can also email us at radio@cgtn.com with your questions or feedback. And stay updated on the latest climate stories with our Substack newsletter, Climate Choices. I'm Zhao Ying. Thank you so much for listening. See you next time.